Blackbody radiation. The first clue to the quantum nature of radiation came from the study of thermal radiation emitted by opaque bodies. As we will see, the observations of the spectrum of light emitted by such objects were not explained at the end of the 19th century by using the classical physics. By the way, if you like this video, don't forget to like and subscribe to this channel and activate the bell. It's very important for the continuity of this channel. A body at any temperature emits electromagnetic radiation. Because they are related to the temperature at which the body is, they are often called thermal radiation. Hot bodies emit radiation, which we experience as heat. Gradually increasing the temperature of a body, it begins to emit visible light, initially red light, then moving on to yellow, green, blue, and at high temperatures, white light, reaching the ultraviolet region of the electromagnetic spectrum. For the study of thermal radiation, a body called blackbody was idealized. The blackbody may be modeled by a box with a small hole. We heat the box up, wait for the system to reach a stationary state at a fixed temperature. See what kind of electromagnetic radiation, intensity as a function of frequency or wavelength, comes out of the hole for the given temperature. The radiation emitted by the opening is called blackbody radiation. The vibration of atoms was considered to be the origin of this thermal radiation, and the process can be described briefly as follows. The radiation absorbed by the body increases the kinetic energy of the constituent atoms, which oscillate about their equilibrium positions. Since the average translational kinetic energy of the atoms determines the temperature of the body, the absorbed energy causes the temperature to rise. However, the atoms contain charges, the electrons, and they are accelerated by the oscillation. Consequently, as required by electromagnetic theory, the atoms emit electromagnetic radiation, which reduces the kinetic energy of the oscillations and tends to reduce the temperature. When the rate of absorption equals the rate of emission, the temperature is constant, and we say that the body is in thermal equilibrium with its surroundings. The electromagnetic radiation emitted under these circumstances is called thermal radiation. The next figure shows radiation emitted by the object at temperature T that passes through the slit and it is dispersed according to its wavelength. The prism shown would be an appropriate device for that part of the emitted radiation in the visible region. In other spectral regions, other types of devices or wavelength-sensitive detectors would be used. The spectral distribution of the radiation emitted by a blackbody is found experimentally to depend only on the absolute temperature T. The following graph shows the spectral distribution at 3 different temperatures. The basic problem was in understanding the observed distribution energy as a function of wavelength in the radiation emitted by a blackbody. By 1900, blackbody radiation had been studied extensively and 4 characteristics had been established. First, the energy intensity increases with increasing temperature. In short, as the temperature of the blackbody increases, the total amount of energy area under the curve it emits increases. Second, as the temperature of the blackbody increases, the peak of the distribution shifts to shorter wavelength. This shift obeys the following relationship called Wien's displacement law. As the temperature rises, the peak of wavelength becomes higher and shifts to shorter wavelength. Yellow light has shorter wavelength than red light, so a body that glows yellow is harder and brighter than one of the same size that glows red. Third, the intensity of energy emitted per unit area at absolute temperature T is proportional to the fourth power of the Kelvin temperature, and it is given by Stefan-Boltzmann law, where sigma is a fundamental physical constant called the Stefan-Boltzmann constant. Fourth, experiments show that the shape of the distribution function is the same for all temperatures. We can make a curve for one temperature fit the other temperature by simply changing the scales on the graph. During the last decade of the 19th century, many attempts were made to derive these empirical results about blackbody radiation from basic principles. Lord Rayleigh and James Jeans at 1890s tried to theoretically derive the energy distribution for blackbody radiation. They started from Boltzmann's distribution. In this equation, N is the number of particles in thermal equilibrium at the temperature T with energy E. The Boltzmann factor is the probability that a given particle has energy E. In classical physics, the energy E can take any value continuously, and there is not any reason to limit it to take only discrete values. This is because the temperature T is continuous and not discrete. Hence, the energy E must also be continuous. We will not perform the calculations here, but the classical theory predicts for the energy density distribution function per unit wavelength is given by Rayleigh-Jeans equation. At large wavelength, this formula agrees quite well with the experimental results shown in the figure, but there is serious disagreement at small wavelength. The experimental curves in figure fall towards zero at small lambda. By contrast, this equation goes in the opposite direction, approaching infinity at a result that was called in Rayleigh's time the ultraviolet catastrophe. In the year 1900, Max Planck proposed a theory that agreed with the experimental data. Planck suggests that the energy of the atoms cannot have just any value. Instead, each has energy which is a multiple of a minimum value related to the frequency of oscillation given by the formula, where h is the constant of proportionality, now known as Planck's constant. Planck's assumption suggests that the energy of any atom vibration could be only a whole number multiple of energy, where n is called a quantum number. Quantum means discrete amount as opposed to continuous. The Boltzmann distribution becomes: if you replace F with C over lambda, we get We now look at the Boltzmann factor. In short wavelength, the probability of thermal agitation is small because of the small value of Boltzmann factor. The low probability of excitation results in very little contribution to the total energy. This low probability turns the curve over and brings it down to zero at short wavelength. We won't go into the details, but the energy density distribution function per unit wavelength is given by Planck's equation. Let's see how it works. Pay attention in this example. To solve item A, we assume the Sun acts as a black body and use Devine's law, replacing lambda maximum with 500 nanometers. To solve item B, we use the Stefan-Boltzmann law, replacing the temperature with 5,800. The enormous value found in part B is the intensity at the surface of the Sun. When this radiated energy reaches the Earth, the intensity has decreased, but it is still impressive. Let's see another example. According to the graph, lambda maximum is approximately 1.4 micrometers. We use Devine's law, replacing lambda maximum with 1.4 micrometers.